Okay, I think we should start. Welcome to everyone to this first session of the ACM conference on interactive surfaces and spaces. My name is Jean van der Donk from Université Catholique de Louvain, close to Brussels, Belgium. It's not UCL, it's UC Louvain now, so in order to avoid any confusion with UCL where Nick is located. Okay, so welcome to everyone. Our first speaker is Joshua Reibert from German Aerospace Center, located in Jena, Germany. In German, DLR, which stands for Deutsches Zentrum für Luft- und Raumfahrt. So usually we are used to say the floor is yours, Joshua, but in this case, we have to say that the display is yours, or maybe the large vertical display is yours. So there you are.
Thank you for the introduction. Hi, so as introduced, my name is Joshua Reibert, and I'm going to present this paper called Multi-Touch Interaction with Parallel Coordinates on Large Vertical Displays, which is a result of a research collaboration between the German Aerospace Center in Jena, as mentioned by Jean, and the Bauhaus-Universität Weimar as well. Large high-resolution displays, also abbreviated as LHRDs, are human-scale environments that offer an increased screen real estate that information visualization has yet to take advantage of. And especially parallel coordinates benefit from this larger screen space and resolution, which allows the visualization of more attributes, improve the legibility of individual items, and reduce clutter to reveal patterns in the data. Working with parallel coordinates, users usually stand back for an overview and then approach an axis or a pair of axes to analyze distributions or correlations in detail, which creates a kind of natural focus and context. Multi-touch interaction is well suited in supporting users to work with the data from up close, but at a wall-size display it comes with new challenges, such as uncomfortable long-range touches, possibly even across the whole screen, and limited physical reach, resulting in uncomfortable crouching for the lower screen areas, as can be seen here in the image, and even no access at all to the upper areas for most users. So we developed a multi-touch vocabulary in an iterative design process to overcome these limitations and to enable users to interact with parallel coordinates, even on LHRDs beyond arm's reach. Our gestures are mainly bimanual and make use of the concept of hold and move to fixate the background with a non-dominant hand and then manipulate an object with the dominant hand. Users can vertically shift axes by holding the background and subsequently dragging the axis. While this will partially move an axis off screen, it brings a region of interest at full resolution into a convenient vertical position for interaction. To complement physical navigation, a horizontal fling gesture triggers a cyclic horizontal scrolling of the axis. The strength of the fling controls the amount of scrolling, and axes that are shifted off screen reappear on the opposite side in a seamless transition. A background hold and a subsequent horizontal drag moves a single axis. To avoid long-range dragging, the axis moves directly with the finger at first, but the distance is then amplified with a hyperbolical mapping after a threshold, and thereby extends the user's reach across the whole display. A two-handed pinch gesture brushes a value range on an axis to select all items in that range. However, even on such a high-resolution display, clutter and overplotting are an issue. A hold and a subsequent drag on the axis ties a value range to the fingers and creates a focus area, whereas the context to either side is compressed. Both the creation of focus areas as well as brushing rely on two-handed gestures for defining a value range on a vertical axis. Since the axis vertical extent exceeds the user's reach, a desired selection is sometimes not possible directly on the axis. But this sometimes only becomes evident during the interaction itself. So as a consequence, we propose a vertical range extension that fluently extends the range using the horizontal distance from the axis, using the same hyperbolic transfer function as before. And this works similarly for defining focus areas as well. Due to contact restrictions, we did not perform a formal user study, but instead invited 4 experts to review and evaluate our system and to find potential usability issues. Our participants used our system with a movie dataset after a short tutorial and a free exploration phase to solve 5 tasks with a think aloud method to comment on their interactions. All our participants were able to use our system and the multi-touch gestures to successfully solve each task with a dataset, and they stated that the interaction vocabulary was suitable to solve such tasks and comprehensively supported them in their visual analysis. Our participants especially liked the vertical shifting of axis, the long-range horizontal axis dragging, as well as the vertical range extensions for brushing and focus areas. Yet they preferred direct interaction whenever possible. And they navigated physically instead of using the cyclic scrolling, since physical navigation does not change the position and order of axes. Furthermore, they uncovered a lack of distinction between the gestures for brushing and the focus areas. In contrast to previous works, our multi-touch gesture set facilitates interaction from up close and yet equips users with the means to reach the whole screen. Our study shows that participants prefer direct interaction when possible, but on such a display that is not always the case, and they appreciated our range extensions, which allowed them to fluently extend a vertical range beyond their physical reach during the interaction. Hold and Move was originally proposed for mobile devices, but we have shown that it works also well on LHRDs and helps to distinguish the target of a manipulation from the background. We believe that mid-air gestures or speech input are well suited to supplement our gesture set with the means of interaction from a distance to then work at a personally favored distance, or even to take turns of using remote and close-up interaction. So with this, I conclude my talk. Thank you very much for your attention and enjoy the following talks.
Okay, thank you very much for your very visual presentation, Joshua. So now we will switch to our second speaker, who is Zhu Fan from CNRS and University of Grenoble-Alpes in France. And the paper is entitled Impact of Hand Used on One-Handed Back of the Device Performance. So during your presentation, Suji, I promise that I will not perform any gesture on the back of my screen.
Okay, thanks for the introduction. I think the backward device interaction has not been well explored, so we will introduce something in that area. Hi. Okay. Hi, I'm Zhu Zhi from the panel. I think. Okay, I will list the panel here. It's not quite a problem. Hi, I'm Zhu Zhi from Grenoble University. I will present you our paper on the impact of hand used on one-handed backward device performance. Backward device interaction attracted a lot of interest in HCI community. Victor and his colleagues used the backward device interaction to avoid the occlusion on the screen. Bodish and his colleagues used the back-of-device interaction to create smaller wearable devices. Lodgefield and his colleagues combine back and front of device interaction to improve the accuracy and speed of target selection. And there are many other researchers use the back-of-device interaction to provide new techniques to enrich users' interaction on the screen. For example, Costa and his colleagues used the gestures of simple typing at the back of device to input emoji. Wong and his colleagues used the gestures of simple swiping at the general public. ZTE designed a phone with a second touch screen on the back, which allows users to make touch input at both sides of the smartphone. Microsoft also issued a pattern for back-of-device interaction. However, we have little knowledge about users' performance at the back-of-device. For example, user performance in steering tasks at the back-of-device was not studied. In particular, it's important to consider one-handed interaction in back-of-device. One-handed interaction is commonly seen in our daily life. Hopper observed more than 1,300 people using their devices, for example, on the street, in airport, in cafes. He observed that when they needed to interact with their devices, nearly half of them used only one hand. And among these people, more than 30% used their left hand. In our daily life, when we are eating, writing, or doing something else, one hand might be encumbered. In these situations, one-handed interaction cannot be avoided. So when we interact with only one hand, what is the difference of performance between our paper hand and the non-paper one? We addressed these questions in our paper, and we focused on back-of-device interaction. Here on, I will present our experiment to compare participants' performance between two hands on one-handed back-of-device interaction. And before we started our experiment, we registered our experiment in Open Science Framework. And you can find all material to reproduce our work with the link below. During our experiment, we invited the participant to sit down in front of the monitor. They turned the touch screen of the smartphone face down to enable back-of-device interaction. They interacted with the smartphone with their index finger, and they can see the position of their index finger on the monitor. We studied 3 common HCI tasks: target acquisition, circular steering, and linear steering. On the screen, the red dot presents the position of their index finger. And in target acquisition tasks, participants slide their finger at the back of device to select target and lifted their finger to enable back of device to enable target selection. If they lifted their finger inside the target, it's a successful selection. Outside the target, it's an error. And each participant made 10 trials with each hand in each motion orientation, motion amplitude, and target width condition. In circular steering tasks, when participant's finger crossed the start line, they began steering. If their finger stroked over the end line without crossing the border of the tunnel, it's a successful trial. Once their finger crossed the border of the tunnel, it's an error. Each participant made 5 trials with each hand in clockwise and anti-clockwise orientations, and in each tunnel length and the tunnel width condition. For the steering tasks, it's similar to circular steering, and the participant steered in 4 orientations: the leftward, rightward, upward, and downward. Here is our result. From the left figure, we can find that participant's paper hand was in average 10% faster in target acquisition tasks, with an average movement time 1.2 seconds versus 1.4 seconds. In 2 steering tasks, the difference was not significant. For the error rate, we found that participant's paper hand was in average 20% more accurate in target acquisitions with an average error rate of 5.4% versus 6.8%. In two steering tasks, participants' preferred hand was in average more accurate. However, ANOVA shows no significant difference. To conclude, in our experiment, we found that participants' preferred hand was in average faster and with more accuracy in target acquisition tasks. But in two steering tasks, the difference was not significant, neither in speed nor in error rate. For our future work, we will study other modalities of the backward-device interaction. For example, in our current experiment, we studied participant performance with their index finger at the backward device. With the new techniques like the infinite touch, we can identify multi-finger at the backward device. So in our future work, we will further study participants' performance at the backward device with other fingers and also with multi-finger interaction. For example, we don't know yet participants' performance with techniques combining index finger and the middle finger at the backward device. Thank you for your attention. I will be happy to answer your questions later.
Okay, thank you very much, Sushi, for your nice presentation. I really appreciate that you made a pre-registration of your experiment on osf.io. I think this should become a more frequent practice. To all attendees, again, please post your question for any of the authors in the individual paper text chat in Discord so that we can gather all your questions in the end of the session. So now we will switch to our first speaker, who is Kai-Sing Zhao from IRIT, Institut de Recherche en Informatique de Toulouse, located in Toulouse in France, but also from Université Fédérale de Toulouse, Midi-Pyrénées. And Kai-Sing will present his paper entitled VibHand, One-Hand Vibrotactile Interface, Enhancing Non-Visual Exploration of Digital Graphics. So perhaps if we don't see your presentation, maybe we can feel it. So the floor is yours, Sushi. No, I'm sorry, Kai-Sing.
Yeah, thank you. I will start my presentation. Sorry. I have a problem with the slides. Okay, I will first. Okay, can you see my screen? Okay.
Yes.
Okay, I will start.
Perfect.
Hello, everyone. I'm Kai-Sing Zhao from University of Toulouse, France. Now I will present our paper entitled VibHand, On-Hand Vibrotactile Interface Enhancing No Visual Exploration of Digital Graphics. This work was conducted with my co-authors Marco Serrano, Pagna Oriola, and Christopher Frey from University of Toulouse and CNRS. As you may know, graphical information, for example, maps, schemas, mathematical graphs, drawings, etc., is very useful for conveying information. However, access to graphics is always a challenging one for people with visual impairments. Generally, for people with visual impairments, they use tactile graphics, as you can see on the left, which are rare because they rely on specific expertise and they are also time-consuming to make. Compared with the tactile graphics, digital graphics presented on touchscreens are more pervasive. They are easily modifiable and can be made interactive. On the right side, we illustrate a study from Tech Lee and collaborators, which shows that it is possible to use a vibration of tablet to explore a simple digital graphic. In their work, the tablet vibration triggered and stays down as long as the explorer finger touches the segment of the graphic. However, the exploration of vibrating digital graphics remains an issue due to the absence of tactile cues under the fingertip. Before presenting in details our study, I'd like to give an overview of VibHand. It combines a tablet and 4 vibrators placed on the back of the hand. As you can see, the graphic is presented directly on the tablet without introducing any other special processing. As in the Tech Lead study, the tablet vibrates when one finger touches a single part of the graphic. Additional vibrations on the back of the hand provides the directional feedback to compensate for the absence of tactile cues under the fingertip. In this study, instead of exploring tactile graphics directly as shown in finger A, or explore with single tablet vibration as shown in finger B, we expanded how to explored how to compensate tactile cues under the fingertip by vibrations on the back of the hand, as illustrated in Figure C. We specifically explored if the use of vibrotactile cues applied on the back of the hand can improve the exploration of complex digital graphics on touch screens. We investigated two types of tactile cues, a pre-cue providing segment direction and a confirmation cue about the exploration progression, as you can see in Figure D. We actuated one vibrator to indicate the top right direction and two vibrators at the same time to indicate the right forward direction. In Figure E, a long strong vibration followed by a long light vibration indicate 40% and 80% of the exploration progression respectively. To do this, first we evaluated several design factors of the vibrotactile interface. The results showed that a vibration duration of 200 milliseconds is enough to transfer directional cues. They also showed that we can use 4 vibrators on the back of the hand to convey 8 cardinal directions. As you can see, we use 2 simultaneous vibrations to represent the 4 basic directions and 1 single vibration to represent the intermediate directions. The layout of the vibrator was another factor that we examined. As shown in the finger on the left, we designed 4 configurations on the back of the hand based on square and cross shapes. We found that the direction recognition task with the configuration C was significantly better than other configurations, as shown in the finger on the right. Our final design of vibrotactile direction and progression cues are presented here. We chose the top direction as an example. The different vibrotactile representations form our vibrotactile interface on the back of the hand. We evaluated the selected design by conducting a behavioral experiment. The aim of this study was to verify the hypothesis that the 2 cues rendered by the vibrotactile interface can enhance digital graphics exploration without introducing additional perceptual or cognitive issues. We recruited 12 participants with visual impairments and 12 blindfolded participants. We designed two different types of digital graphics, simple geometric graphics as shown in set A and B, and the non-figurative graphics as shown in set C and D. We used the delete matching to sample task in our study. In each trial, we asked the participant to explore a sample graphic and an alternative graphic after a 5 seconds delay. They had to judge if the 2 graphics were identical or different. We compared 2 interaction techniques, the control condition which was based on the technique proposed by MacLeod and Vibrotactile. The experiment included 2 phases. 2 phases to get familiar with the direction and progression cues respectively. After familiarization, the participants were presented with 2 blocks of the trials, the first one with the geometric graphics and the second one with the non-figurative graphics, because it corresponds to increasing difficulty. The interaction techniques were counterbalanced across the participants. In total, we recorded 384 trials corresponding to the exploration of 2,716 segments. We analyzed 6 different methods. In this slide, I first present the identification of geometrical graphics. Actually, the results show a significant effect of the interaction technique, but no effect of the visual details. For the pair comparison, there was a significant effect of the interaction technique too, but there is no effect of the visual details nor the graphic time. The response time is the time needed to see if the second graphic is the same or different. As you can see on the finger, the response time is shorter with left hand. The ANOVA shows that there is an effect of the interaction technique and the graphic type on the response time, but no effect of the visual details. The unrelated figure path is the difference between the exploration path and the graphic length. A larger unrelated figure path shows that the exploration strategy is not optimal. You can see that the unrelated figure path is much shorter with the right hand. The ANOVA shows that there is an effect of the interaction technique, but also of the visual status on the unrelated figure path, but no effect of the graphic type. We observed the exploration movements that were made with the 2 techniques to understand these results. The lower figure shows that the exploration with right hand presents more linear finger paths and more efficient transitions at the end of the segment. In fact, right hand helps to execute more efficient exploratory finger movements. Finally, we compared the acceleration speeds. The acceleration speed is the average speed measured for each condition. The finger shows that it's significantly higher for people with visual impairments, but it's also higher with the web hand. Our experiment confirmed our hypothesis that web hand improves non-visual digital graphic exploration from different aspects. However, we didn't observe any difference on the identification accuracy of no graphics, nor on the comparison accuracy. In the future, an important question is to compare the exploration with web hand and with regular tactile graphics. Actually, we do not believe that web hand would outperform tactile graphics, but we make a hypothesis that web hand would provide users with visual impairments with ubiquitous, useful, and convenient access to digital graphics in many real-life contexts. Thank you for your attention, and for more details, please refer our paper.
Thank you very much, Kaisen, for your presentation. Please stay tuned. We will have maybe some questions in the end of this session. So now we will move to Cédric Honnet from CENIMA and I3N, and also from University of Lisbon. He will be presenting a paper from CHI 2020 entitled Polysense, Augmenting Textiles with Electrical Functionality Using In Situ Polymerization. So Cédric, you can start when you want. Thank you very much.
Can you hear me well?
Yes, we can.
Just a little correction. Anna Batista is the one from currently at MIT Media Lab. But it's a collaboration with plenty of people in Germany. So hi, my name is Cédric Honnet. I'm going to present Polysense to make. Is it better? I'm going to try my best. So, and I'm going to present Polysense, a quick and simple process to make e-textiles with various sensing properties, such as humidity, temperature, pressure, stretch, capacitive sensing, but it can also heat. So this presentation will be chronological. Let's start with the origin. So this project was while making...
Cédric, sorry, could you keep the mic closer to your mouth because it's a little bit cut. I'm sorry. Okay, go ahead. Sorry.
Okay. So this project was making this e-textile pressure meter. As you can see, multi-touch that uses pressure as information. So this matrix uses two kinds of materials. Textile electrodes that we can see in white here, and a resistive material. It changes its resistance when someone presses it. This material was expensive, about $200 per square meter. It became harder to get at the time. But what is piezoresistivity anyway? We take the material as a layer of free conductive parts. They are pressed or stretched, the overall conductance increases. So we tried to make our own, but we realized that we didn't really understand the material. Fortunately, I was invited in a material scientist lab in Portugal. And after various analyses, such as Raman spectroscopy, we understood it better. It only needs two chemicals, a monomer called pyrrole and iron chloride. Here, we use a magnetic stirrer to mix the textiles with the chemicals, and we obtain a pressure sensor in about 1 hour. Okay, you might want to see what is possible now. In this application, we augmented off-the-shelf gloves to control the 3D model of a virtual hand. We appreciate that this off-the-shelf kinesiotape can be functionalized for on-skin interfaces, including this linear slider. Here, we can see a touch and visual installation that uses several meters of our functionalized fabric. It still worked perfectly after many months maybe a few months in a museum, and then in Ars Electronica more recently. In both places, it was touched every day, all day. So the process is reliable over time. In this other artistic application, we polymerize feathers and use them as a capacitive sensors for sonified installation. The publication focused on textiles, but as you can see here, it works on almost anything porous or fibrous. So for example, it's also good with wood, cork, paper, or foam, just examples. We also augmented the pair of leggings to control the presentation slides. Thanks to the warm conditions, we realized that our process can also sense sweat really well, or humidity. Polysense can also be used as a custom actuator. As anything resistive, this polymerized glove heats when electrified, but temperature affects electrical resistance too. So we characterize this resistance variation as a function of temperature to avoid burning the user, for example. You just saw a few polymerizations that we deployed in various museums, festivals, or conferences. Now you might want to do your own. So here's a quick process. First, use a bit less than twice the water needed to soak all the fabric or materials that you want to functionalize. Second, add the monomer. Here, it's pyrrole again. Then soak the fabric and mix for about 10 minutes. Finally, add the oxidizing agent. Again, it's iron chloride. That's what triggers the in situ polymerization. For piezoresistive sensors, keep for about half an hour, and for capacitive sensor, maybe 2 hours at least. Needs more conductors. Okay, let's talk about some design methods now. The traditional technique called shibori allows efficient and simple masking. It also enables repetitive patterns, but the most unique possibility is gradients. This Indonesian technique called batik consists of using the mask. It enables quick sketches. And we measured resistances with simple traces as on the sample here. This batik process also works for etching copper with acid, and as in many PCB fabrication process. So we created a full circuit with conductive and sensing parts. This hybrid approach here allows measuring horizontally or vertically. The flexibility of textile also allows making foldable sensors. Here, C in red can be folded to touch B to measure a variable resistance between A and B. You can see a bit on the right. So you saw all the possibilities, or the possibilities that we did, and I would be happy to exchange about more technical details or potential next step if you're interested. Thanks for your attention.
Okay, thank you very much, Cedric. I think that polymerization has a lot of applications, as you properly demonstrated. We'll talk about that later in the end of the session. So now we'll move to our fifth paper, also an invited paper from CHI 2020. It will be presented by Michael Wesley from MIT Computer Science and Artificial Intelligence Lab, located in Cambridge, USA, of course. And the paper is entitled Sprayable User Interfaces, Prototyping Large-Scale Interactive Surface with Sensors and Display. So maybe I will spray my user interface as well after your talk. Please go ahead.
Thank you very much and welcome to this talk. Ask you to start your video. Okay, does it work? Yes, perfect. Okay, so yeah, thank you very much, Jean, for the introduction. And today I want to talk about this question: how can we actually prototype large-scale interactive surfaces? And I first want to start with some question that we raised in the beginning, and right. And this is how can we actually make large objects interactive? And so if you think about it, this can actually be quite challenging question. So if you would, for example, try to make an interactive object, very often you would use some kind of a fabrication device, right? So this could be like a 3D printer, for example. This could be a laser cutter, a milling machine, a screen printing frame, you name it, right? So, but what have all of these fabrication devices in common? So, and this is that they always have like a limited fabrication volume. So like if you want to use a 3D printer to fabricate something interactive, it's really hard to like actually like print something that's larger than the 3D printer. So this is like an inherent limitation that all of these devices have. So, and our solution that we found for like making like really large objects is based on a spraying technology. So what we use here and what you see here in the video is an airbrush system. So we spray here a conductive ink, and you see this is like not limited to any like size restrictions or so, because it is a handheld device and it is a contactless fabrication technology. So as long as you can like reach it somehow with the arm, you can fabricate it, right? So what you can see here is like not only like conductive materials, functional materials can be added, also like aesthetic designs, and you can integrate it into user interface as you see it right here. So this blinking thing is a sprayed touch display. And once you touch it, you can turn on your lamp, for example. And we integrate into this like sprayed spray can, 2 touch sliders, and then by like sliding up and down on the body of the spray can, you can change the brightness of the lamp. And with the second slider, it's integrated into this like beam that comes out of the spray can. You can also like set the color. And I want to like show like a few more examples of what is possible with this technology. What you see here is an interactive sofa. So we sprayed here with a transparent conductive material that like fully integrates into the design of the object, so you can't see it anymore. A bunch of like touch sensors. So when you sit down, the system recognizes that like a user is there and like starts a photo album. And we integrated like 2 proximity sensors in the armrest. And when the user's then like sliding to the left and to the right of this armrest, you can like navigate through the photos that you have in the app. And once they get up, the system recognizes this as well and can turn off the photo app. So in the third example, this one has sound, so I might be a bit silent for the next one. This is an interactive music player. So like we sprayed here like on a concrete pillar, a bunch of touch sensors, and they are connected to like a music interface. And when you touch it, it starts in music. I turn off the sound again because the illustration should be there. So like what is interesting here is we sprayed this on a concrete is like a very rough material, which is usually like very challenging for all kinds of like printed electronics or like working with conductive inks. And second is this was inside the MIT C-Cell building, and I just like sprayed it and they didn't fire me, which was like a very positive point of this. All right, so this technology is like very accessible, and this was like one of the main focuses that we had for this work. So we wanted to make it with materials that are all nicely accessible. So what you need like to replicate this entire system is an airbrush system. So this consists out of a compressor. So you work with compressed air. And an airbrush gun, which is like using this compressed air to like create like a fog pretty much of ink. It has a little container on top. You can just like fill it with like all kinds of inks and then spray it on a surface. And then the second part of the system, and this is like pretty much like what makes it different to traditional airbrushing, where you usually use just like colored inks, right? And we use functional inks here. So they have like specific properties. So they can be, for example, conductive, which enables you to like create traces, to create sensors and all that stuff and more. And I will go more into detail in one of the next slides. And then, of course, like most important, always like when you work with like these kinds of materials is like safety equipment. So since like you're spraying, you're creating a fog that you can breathe in. So you should always like wear a mask. You should wear safety glasses, and you should always wear safety gloves. All right. So the first material that we use here are conductive inks. So we show like here a single layer fabrication techniques. And on the left-hand side, you see a copper ink. This is a highly conductive ink that can also be used for high current applications, for spraying wires that like go over like a larger area where you like need like a pretty high conductivity to like get clear signals. And on the right-hand side, you see also a clear conductor. So this is like a transparent conductive material, which is very nice to like integrate the user interface into an object and not change the appearance of the object. So to integrate it seamlessly. And what you can create like with these kinds of conductive materials is a set of design primitives, so to say. So for example, these can be like touch and proximity sensors. These can also be continuous slider elements. And of course, like every time when you have like interactive elements that you want to integrate into a 3-dimensional object, you also need wires, of course, to connect it to a power supply, for example, or to connect it to a microcontroller. So you can also like spray a microcontroller connector. So, and like you can see here in this video how this can look like. So we also designed a design toolkit, and it features a projection which like is guiding the user in like spraying these interfaces. So we like use here this transparent conductive material and like spray it on the surface of this couch. And you can see like after we finished spraying everything and we let it dry for a little bit, you can see that it's conductive and like nearly invisible. So we also feature a multi-layer fabrication technique. So this is about like electroluminescent displays. So just in short, to summarize like how this like roughly works is we have a phosphor material there. So this is a light emitting material. And once you put it into an electric field, it starts to glow. So this is like the basis behind it. And you have to like sandwich it between two conductive layers to create this electric field. So if you put it under an AC current, this phosphor starts to glow. And you also need a dielectric to like isolate these two plates from each other. And you can see here in this example how this looks like. You can also like see another feature of the user interface that we created here. It's like automatically generate these stencils that you see right here. And then you just like spray these like conductive inks like layer by layer on top of each other. So first a conductive layer, a phosphor layer, this you see right here. Also a copper bus, which you need for like large interfaces. You want to like distribute the energy evenly, so the displays also like have a uniform brightness everywhere. And then you spray like the clear conductive material, which of course need because otherwise you couldn't see the phosphor, right? So you see here in this example how this can look like. So now we come to the limitation opportunities. Usually my favorite slide, like what comes actually next, like what else can we do? And so on the one hand, we want to like focus and investigate like more about like functional materials and about more interactive elements that you can integrate with like this spraying technology. One example, but there are like many more, but one example are electrochromic displays. You can, these are like color changing inks that change their color under a specific current. It's like a little bit similar to e-ink. So, and especially from material science, there's like a lot of stuff that now like swaps over to HCI, which is a super fascinating area at the moment. The second area that we want to focus on is like interactive architecture. So what we have presented in this project so far are like room scaled interactive surfaces or user interfaces. But how does it actually scale up if you want to go like really large? So like what if you want to make the facade of an entire building interactive? As you can see like in here, here in this picture where like these gold plates on the facade like change the appearance of this building controlled with motors. Then this of course like also leads directly to like how can we integrate actually like electric components into these user interfaces, and how is this possible? All right, so and with this I want to end my talk. Thank you very much for listening to it, and please post your questions in the Discord channel. We'll be happy to have some. Thank you very much.
Thank you very much to you too, Michael. Very impressive. It looks like almost any surface could become interactive based on your technology.
Yes, it
almost. So now we will switch to the question and answer session. So again, for all attendees, please feel free to send your question to the Discord channel. And we will start with a first question to Joshua. Joshua, a question from the audience. How do you envision collaborative usage of your PCP application on large displays? In your demo, you showed just one person at a time.
Yes, correct. That is a limitation of this work right now. So we only tested it with single users. But of course, some of these techniques already work with collaborating users. So especially in close collaboration, this is possible. But of course, especially the interaction techniques that have a global effect on the visualization, they collide with collaborating users. So like, for example, the navigation and the reordering of the parallel coordinates. So that can be problematic. But I think that users have to like coordinate their interactions there. Like if you're discussing in a group, then you can't always talk, and you have to coordinate and watch each other. So there needs to be some level of coordination. But of course, it would be nice to have some form of loose collaboration, and especially the Interactive Media Lab in Dresden has done some great work there, supporting this distant interaction with such large screens. So multiple coordinated views are, of course, suitable to support also a looser form of collaboration on such displays. But I think it's important to fluently transition between these loose collaborations in different views on such a display, and then again work together on one large visualization to really take advantage of the additional screen space we have here available.
Okay, but basically you're able to afford it since your technology is multi-touch, right?
Yes, in principle it's possible. So it's only a matter of if two people at once start scrolling the axis, then of course they will just move it around, and nobody will really gain an advantage of collaborating here. So they have to coordinate their actions right now, and this would of course be possible, like to have to duplicate this parallel coordinates visualization, so both can work on their own, and then maybe return to working on one large visualization again.
Okay, thanks a lot. Now we have another question from the audience to Shifan. How did you recruit your participants, and were they left-handed or right-handed, and did it influence the result?
All our participants are right-handed, and in total we have 12 participants. We have 12 participants because this number is a very popular number. Started by Kelly Kayan in the paper of local standard for sample size in HCI. In CHI, say why we choose this number of participants, and as we have 4 equal days for our experiment, but finally we found that most of them are not satisfied. So we cannot really tell whether the number of participants will influence the result.
Okay, sounds good to me. Thank you. Now we have also another question from the audience to Kai-Xing Zhao. In the example that you have shown in your presentation, there are basically strokes that consist of a single line. There were no forks, right? So what do you think of mappings when the user are facing a fork, for instance, left versus right?
Yeah, yes. In fact, currently all the graphics is single direction, is single line, and we did investigate this type of question. For example, we propose to give a Vibrotactile pre-overview. That means when they face a fork, we can give them an overview of the next several directions. And they can, from our preliminary studies, that participants were able to memorize several next directions, and they can choose they want to go left or go right. So it's called Vibrotactile overview.
Okay, sound good. Now we have a question also to Cedric. In the example that you have shown, well, of course, your technology is sensitive to pressure, but do you think that you can capture something like squeezing gestures, like, for instance, on interactive cushion?
I'm sorry.
I'm sorry, I can't hear you. Would you like me to repeat the question, Cedric? I can't hear you.
What about better?
The audio is a little bit sloppy. Can you hear me?
Okay. There is a different mic.
Okay, so I'm repeating the question. Can you hear me? Yes. So you demonstrated that your technology is, of course, sensitive to pressure. Do you think that we could create something like an interactive cushion where I can sense squeezing gestures if I fold the cushion or if I turn a corner with pressure. Do you think you are able to do that? I can't hear you. Did you switch your microphone on? I'm sorry, I still can't hear you. I don't know. What about the others? Ah, okay.
Ask a question to someone else. I take a microphone. Okay, can you hear me now?
Okay, Cedric, could you keep the question in mind? We'll switch to another question and come back in a few minutes. Is it okay for you? We have a question to Michael. Michael, when you have demonstrated some swipe gestures on the coach, right?
Yeah, this is correct.
Do you think, well, this is an example among others, do you think that people will perform the same gestures on the coach as they are used to produce with other devices? Yeah, so there is, of course, the problem of legacy bias, is that people tend to reuse the same actions or the same gestures that they know. Or do you think that there will be any difference?
Yeah, so this is actually like a great question. So this entire like large scale fabrication stuff, there is like a little bit of related work in HCI, but it's like a little bit like unexplored. And that's what we wanted to kind of like produce like a platform that like other researchers can do like more research about like what kind of interactions, what kind of gestures actually make sense for like large user interfaces. So like what one example that I like think at the moment like a lot about is, for example, like, you know, usually we talk about like, you know, having like a pinch gesture or having like a touch sensor or something on a 3-dimensional object, right? But if we really talk about large scale user interfaces, and I was like starting this a little bit with my outlook to future work, what about interactive architecture? So like when we want to make like the facade of a building interactive, then like a touch sensor and 5-meter height doesn't make so much sense. So like, what does it actually mean? What kind of interactions and what kind of interaction like with the human or with like some intelligent system would it actually create if we can make like extremely large user interfaces? And that's what we also want to focus in the next years and the next conferences and next papers on, to explore this area more. You're muted, John.
Your example with the facade makes me thinking about the so-called mass computer interaction, where you have a lot of people in front of a very large surface, like a facade or a building. Do you plan to cover something like that?
The first project that we've seen today actually also like corresponds. I mean, like this entire research area about like large scale displays and how to interact with them actually like pretty much goes in this direction. But of course, like a display has like kind of like a different affordance. So this like more about like having high resolution on large surfaces and then enabling touch. Like this spraying technology is like certainly like a little bit different in its nature. So it's like still open to explore like what it is. So like one example that I always like have, and it's like a little bit cruel example to be honest, and like my friends, when I like presented them the idea, like asked me like what kind of issues I have. So but it is also like a little bit funny. So I was like thinking, you know, like when you think about like, you know, like having sensors like on the roof of a building, then most likely it's actually not for humans. It might be for animals potentially. So like you have pigeons, and, you know, they're shitting everywhere, and you want to avoid this, of course, in your beautiful new building, right? So you could give them like a little electroshock or so. So this is of course you don't implement this, but it would be like one direction, like how, like in which direction interactive architecture could go.
Mm-hmm. So you should introduce a new paradigm. Instead of human-computer interaction, is that it should be anybody or any living body
yeah, an animal-computer interaction. Yeah. There's also food
Okay,
computer interaction.
We'll
So
go back
yeah.
to Cedric. Thank you very much, Michael, again. Cedric, can we go back to you with respect to the question about feeling or sensing squeezing gestures?
Just to check, do you understand? Do you hear me now?
Yes, perfect.
Oh, great.
So
yeah, I can answer
the question.
No, basically the idea was to be able to functionalize anything. At the time, I was focused on making a matrix to do gesture detection, recognition, finger tracking.
Yes, but imagine, for instance, you have an interactive cushion, and maybe you can pressure or you can squeeze the cushion, and then you can probably, I imagine, you can detect
of course.
that.
Yeah. So I was saying that as we could do a matrix with a complicated kind of gesture recognition, we could also do more volumetric things. I can show briefly. I have a sensor here, so it's basically a matrix made out of conductive and piezoresistive element, and this is something that I functionalized, and so this could totally be in a question. If that's answering the question, I can go for the details.
Okay, thanks a lot. I think this is very promising. Joshua, we have a second question for you. In the video that you presented, it looks like you have basically Sankey diagrams with flows and continuous scales. Is it a restriction of your work, or is it just as an example? For instance, what do you have if you have to consider non-continuous scales?
Yeah, so it's actually not flow, but it's each item is a polyline itself. But of course, yeah, non-continuous scales are always or have always been kind of a problem in parallel coordinates. And in the end, you have to have some mapping to numbers. So the simplest way is, for example, if you have a category, like in the data set we used of movies, we had a language attribute, the original language of the movie. And in the end, it was just, so every language received the same amount on this axis. And in that case, if you have such a mapping, it's also possible to use, for example, this vertical axis similarly. So it doesn't really make a difference. But of course, in the end, it would be desirable maybe to adapt these techniques, especially for such categorical data, because then if you don't want to select really a range, but rather, I don't know, maybe you have a threshold of a few centimeters and then you also select the next category as well. So yeah, that there's room for improvement for such scales.
Okay, well, that makes sense to me. Sounds good. Thank you. A question now to Sushi Fan. Sushi, can you hear me?
Yeah.
In your experiment, you basically tested 3 types of tasks, like target reaching, linear steering, and circular steering. Do you think it would be appropriate to consider something like trapezoidal steering, where you have, instead of a tunnel or a circle, when you have something that is progressively more constrained in space? Do you think it would be appropriate to test that?
Yes, we can do that. In our experiment, the tonal width rest constant, but as studied by Johnny Echo and Shumi Jia in 1997, he had in the paper he first proposed the Sturm law. He had studied this question. His results show that if the tonal has the width non-constant, we can decompose the tonal into several tonal with different widths, and we can analyze Shack party by Shack party.
Okay, but in this experiment, they didn't test that on the back of the device, right?
No. In our experiment, all the target width, all the tonal width is the constant.
And do you believe that the surface of the device would play some role? If, for instance, I have to perform an action on the back of a tablet, I would have more space than maybe on a smartphone. Do you think that this would change, or maybe not?
No, I think it's not a challenge.
No, not much. So the form factor does not influence very much, right?
Yeah. Mm.
Okay. I think we are almost done. So the time is now 4 p.m. my local time. So on behalf of the ACM conference and the committee, I would like to, and of course on behalf of the attendees, I would like to say a big thank you to all presenters and for answering the question. And we wish you, of course, the best for your future and good luck for everything. Thank you very much for participating, for submitting your work to ISS, and we look forward to seeing you maybe in other circumstances, maybe in physical shape. Right? Good luck, and thank you very much.
Thank you.